Hey everybody, let's do the partial fraction decomposition walkthrough video. Um, I normally just do the homework questions only, but I think I'll probably run through those few day two classwork questions because I just don't think we'll get to them in class. So I'll do them here, and hopefully that'll be good. You guys will understand everything and be okay. But let's go. I'm not going to do any of the day one classwork because we've done it. It took us 4 days to do 4 problems, but that's okay. You've got your distinct linear factor problems. I think those are straightforward. The quadratic factors you guys are fine with. Um, and you guys now know how to deal with repeated factors too, I hope. So whether those factors are repeated linears or repeated quadratics, you should be fine. And we saw in example 4 that sometimes even, something that seems complicated turns out to be really quite easy. Example 4, we got the values for A and the values for B right away because we only had the one cubic term to pair up with the one cubic term. So A had to be 4. So looks could be deceiving. Something like this that looks like it's going to be really, really complicated actually turned out to be pretty simple. So hopefully you'll be fine. Anyway, we'll get into the homework now. Something like number 1. I don't know. Maybe I've already talked about it, but we'll do it anyway. We'll do all of these. Let me buy myself some extra space real fast. Cram that up there. Probably shrink this down too. Y'all don't need to read that, right? Make that bigger. Okay, so let's do it. We know that our first step is to factor, and you really only want to factor the denominator. Well, okay, since the numerator is 2, you're obviously not doing anything with it. But even if the numerator was, a factorable quadratic, you'd leave it alone. Even if there was some number that you could factor out, you still wouldn't. Because the way this process works is we pair off those coefficients. So you don't want to do anything that would change those coefficients or take it out of expanded mode. You just leave the numerator alone. The denominator, though, you factor. And this is a pretty easy one. You go minus 3. You'll go x minus 5. Now that you got those factors, you'll go ahead and start doing the decomposition. You know that if you have 2 distinct factors in your denominator, then you'll need 2 fractions in your decomposition. One of those fractions will have a denominator of x minus 3. The other will have a denominator of x minus 5. Then we said you'll sort of fill in the numerator with some expression that represents whatever could go into the numerator. Now, since our denominator is linear, the numerator has to be 1 degree less than that, which means it can only be constant, which means the only thing I can put up there really is an a, representing just a single number. But there wouldn't be any x terms up there at all, so you just need an a. Now over here, it's another linear, so you just need another number. It can't be a again, it's got to be a different number. Now using a and b, could it turn out that a is 4 and b is also 4? Sure, right? Using 2 different variables doesn't mean they couldn't come out the same, but using the same variable twice does mean that they could not come out to be different, and that's bad. That ties our hands, so you don't want to do that. So using 2 different variables allows for you to actually get 2 different answers, or just get the same answer twice. So this is the more open-ended thing. We got to do that. All right, what do we say to do now? Now from here you multiply through by this LCD. Just like if we were solving an equation. And multiplying through by this, when it distributes over here, both factors cancel, so you just get the 2. Here the x minus 3 cancels, so you get the a times the x minus 5. And here the x minus 5's cancel, so you get b times the x minus 3. So now that we're here at this point, you can choose to use one of 2 methods. So here you can use systems of equations, or you can use a completely different method, the method that we called let statements. That's probably a better name for it, but this is what we're calling it. So I think at this point maybe I'll duplicate this page so that we can do it both. I'll only do it both ways one time. And then after showing you one problem by both methods, we'll kind of just, from then on, we'll just try to choose the optimal choice. But I'll do this one twice so you guys can get a feel for how both methods work. So what am I trying to do? I want to see the browser. Then I want to duplicate this page. Okay. So now, with all that said, this time let's go ahead and let's do the system of equations first. So to solve for a and b by a system of equations, you would take the a and distribute it in. You'd get ax minus 5a. Then you'll take the b and distribute that in. You'll get bx minus 3b. Then the idea is you want to get your terms together, your like terms. So you go ax and bx. And then you get your constants, the minus 5a, minus 3b. Then you want to combine your like terms. So the ax plus bx can be rewritten as, technically what you're doing is you're factoring out x. So normally you would write it as, x times a plus b, but I actually would want to reverse that. It's multiplication, so of course I can, and I would just write it as a plus b with the x coming second. The reason I want to do that is just so that it's more reflective of the fact that what I have is an x term whose coefficient is a plus b. Because this process is all about matching coefficients together, okay? Now this thing here, that's my constant, all of that. So I might actually turn it into like plus negative 5a minus 3b. And then kind of put parentheses around that. So I can see what I've got now is sort of coefficient times x plus number. And what's a little weird about this problem is there is no x term over here. So that seems to imply that what you've got is 0x plus 2. But from there I can match up my coefficients. So basically I know that if the coefficient of x is 0, then a plus b must equal 0. And that generates the first equation of my system. That a plus b equals 0. Then the constant generates a second one. I see here that my constant is 2. And I see over here that my constant is negative 5a minus 3b. So that means that negative 5a minus 3b is equal to 2. So I've got myself a system now, which you guys should have learned in Algebra 2. And there's, a couple methods for solving systems, but the method that I still prefer is that method called elimination by addition, which is the method where you just try to add the two equations together, and you hope that either the a or the b cancels out, and then you can solve for the one variable that's left. So I can see that if I had a coefficient of 5 on a, then the a's would cancel out. Or if I had a coefficient of 3 on the b's, then they would cancel out. And there's a rule with systems that says you can multiply these equations by anything you want, right? If a plus b equals 0, then I could absolutely multiply through by 3. I just have to make sure I do it on both sides of an equation. You can always do that. You're doing it to both sides of the equation, so the equation stays in balance, so to speak. The equation stays true. So what I'm doing is I'm going to do that multiplication. That generates essentially a third equation, which is just sort of an alternate form of the first. But I'll get positive 3a plus 3b equals 0. And then what I'll do is I'll add this second equation, the negative 5a, blah, blah, blah. I'll add it to the 3a, blah, blah, blah. And then we'll get an equation where the b's cancel. So those are gone now. And I now have negative 2a, and it equals 2. So dividing by negative 2 tells me that a is negative 1. Now, I can take that negative 1 and just plug it into any of these equations. The top one seems simplest to me. So I kind of tend to just like draw a little arrow, and then the negative 1 gets substituted in. So instead of a, I've got negative 1 plus b equals 0. So to solve, I'll add 1 to both sides, and I'll get b equals 1. And so now that I have both of the values of a and b, then your final answer, you'd come back up here. This is your partial fractions. This is our expression decomposed into its partial fractions, right? We've got a fraction and a fraction. Those are the partial fractions. So your final answer is what you get when you substitute these values in. So a means that the numerator of the x minus 3 term should be negative 1. And the b is telling us that the numerator of the x minus 5, oh my god, that's a 4, 5, would be 1. And you guys know my feeling about leading negatives just kind of floating around. Just flip this. Just do it as 1 over x minus 5. And then make it minus 1 over x minus 3. And that is just a slightly neater way to give your final answer. But that's it. That's our final answer. It's 1 over the x minus 5 minus 1 over the x minus 3. And again, this was done by the method of systems of equations. And this method was, I think, by far the worst way to go. So let's do the whole problem again, this time using let statements. Uh-oh, trouble. Okay, these tiles were just out of order. So, view, browser. I just want that one to come second. Okay. So again, both of these methods have the same first few steps where we have to factor, split it into the partial fractions, multiply through by the LCD, and then once you land here, as soon as your denominators are gone, that's when you make your decision about which method you're going to use. So in the let statements method, you're going to literally write a statement with the word let in it, and you're going to let x equal. You're going to let x equal some value that would cause these variables to get canceled. It's really the same. Back here, we canceled out our variables by writing a system and using a method called linear combinations, where we multiplied by something to make the coefficients opposites so that when we added them, they canceled out. When you're writing a let statement, there's an easier way to do that. We can see here that a will basically go away if we just let x be 5. Because if we let x be 5, 5 minus 5 will be 0, a times 0 will be 0, and that whole term will essentially just go away. So you say let x equal 5, then the whole equation will turn into a 2 that equals a times 5 minus 5 plus b times 5 minus 3. So the 5 minus 5 makes 0, a times 0 is 0. It's safe now to say that that whole thing just goes away. And 5 minus 3 is 2, so this is 2b. You divide by 2 and there's your 1. Now, if you want to find the next one, you just write another let statement. Why am I making that dash? That's weird. But you write another let statement, and this time you let x equal whatever value would turn this b into a b that's getting multiplied by 0. So in this case 3. And then you say, alright, well now if we were letting x equal 3, then our equation will become 2 equals a times 3 minus 5 plus b times 3 minus 3. So this is 2 equals negative 2 times a. And it's safe to say now that this whole thing is going to go to 0. So technically, plus 0. But you divide by negative 2 now, you get your negative 1. And now that you have both values, again, we just we grab our partial fractions that we decompose this thing into, and we substitute those values in. Again, we can kind of plan ahead this time. We know we want the b term to come first because it has the positive value. So it'll be 1 over the x minus 5 minus the 1 over x minus 3. Anyway, this is two different approaches to the same problem. Is one method better than the other? It depends on the problem. Some problems, let statements are going to be great. Some problems, let statements aren't going to work at all, and you really have to use systems of equations. I think I told period 8 that on the quiz I'm gonna ask on the quiz that you use each method at least once. So you have to make sure you understand both. Okay, you can't just lean heavily on one method. You better know them both, because on the quiz I'll ask you to use both. And if I don't see you using one method or the other, then you'll lose points for that. So make sure you understand both. Okay, let's move on. After doing number 1, I'm going to try to move faster now, because now you guys get the gist of it. So here goes. Okay, so for number 2. Alright, so same as before, you'll factor your denominator. This becomes 1 over x times x plus 2. Yeah, sure, x times x plus 2. That's so bad. That's so bad. Okay, then you decompose this. You know that you're going to need one fraction whose denominator is simply x, then another fraction whose denominator is x plus 2. This is linear, so just put a constant in the numerator. This is linear, put another constant in the numerator. And we're looking at something that seems to be pretty simple. So you'll now multiply by the LCD. You get everything to cancel here, so we just get 1. Here the x's cancel, so you get a times x plus 2. Then the x plus 2's cancel, so you just get b times x. And we see here that the method of, let statements should work really nicely again. So we'll go let x equal -2. Then we would get a 1 that equals, this whole thing would cancel. So we would just get b times -2. So you divide by -2 and you get -1/2 equals b. And it dawns on me, this is something we haven't seen in class. And that might mean that you guys aren't doing your homework, because you guys should have done your homework, and somebody should have said to me something about, hey, what do I do when I get a fraction? And to your credit, I think there was one kid out there that did. Are we going to do our first shout out? Our first in-video shout out? Nah, we'll let that kid go under the radar. But anyway, to you, that one kid, I appreciated you for actually tracking me down and asking me that. Anyway, we can find the value of a now by letting x equal 0. Then 1 equals a 0 plus 2 plus b times 0. So 1 equals 2a. So now a is 1/2 too. So if I just substitute these in, then I'm going to have, what, 1/2 over x? That's a compound fraction. Maybe you guys didn't ask me about this because you understand compound fractions so well. I doubt it though. Since this is negative, I'm going to just let the negative turn addition into a subtraction problem. And this will be a 1/2 over x plus 2. And yeah, I would require you to clean this up. It is easily done. You just multiply both of them by 2 over 2. You're always allowed to multiply by 2 over 2 because 2 over 2 is worth 1. You're just multiplying by 1. 5 times 1 is still 5, right? 17 times 1 is still 17. So you're not really changing anything. So I can multiply by 2 over 2. Now this 2 would multiply by the 1/2 and give me a numerator that is 1. But my denominator turns into 2x. That's fine. I don't care that my denominator isn't x anymore. It can be 2x. That's fine. That's still considered simple. And that's preferred. So the same thing happens over here now. We get 1 over, I think I'd leave the 2 factored out probably, 2x plus 2. I guess that's one way to tackle it. But looking at it now, it dawns on me, maybe we could just factor out the 1/2. And then just have 1 over x minus 1 over x plus 2. Maybe I prefer that. Maybe this blue answer is more ideal. Let's say this. The blue answer's fine, the red answer's fine. And if you leave your answer in the green version, you're gonna lose. You're gonna lose a point. Because that you can't have complex fractions. Complex fractions are bad. So whether you want to multiply by the reciprocal, I guess technically that's the reciprocal, but basically you're just multiplying by the denominator to get the denominator to cancel. That kind of moves the 2 down into the denominator. This is fine. I would say that the blue is better, to just have the cleanest possible answer here, and then just have the 1/2 factored out. Alright, I said I was going to go fast. I'm not going fast. Let's go faster. Here's 3. Okay, factor your denominator. I hope you guys are good at factoring quadratics with leading coefficients by now. I think we've literally seen this exact one like multiple times by now. But 2 times 3 is 6. Or technically -6. So to get a 5, you'd use a 6 and a 1. You want a +6, so put a +3 here. Now your outer product is +6. Put a -1 here. Now your inner product is -1. So your first will give you the 2x squared. Your outers are giving you 6x. Your inners are giving you -1x. So that's a total of +5x. And the 1 and the 3 are giving you -3. So we're factored correctly. So this is another quote-unquote simple one where we just have the 2 non-repeated linear factors. So you know you're just going to have a over one of those factors, probably the 2x minus 1. Then you're going to have b over the x plus 3. At this point, you probably understand that we're multiplying through by the LCD. So you don't have to show it, right? I was showing it because I'm the teacher trying to make sure you understand. You don't have to show this. If you understand what's going on, then just do it. So this would become just the x plus 17. This would be a times the x plus 3. And this would be the b times the 2x minus 1. And again, let statements seems to be the way to go. If these factors have nice, easy to find zeros, then use them. So we're going to let x equal -3. Now this time, our expression in our numerator before had been constants. It was like just 2, and it was just 1. But now there's an x here. So when you're plugging at -3, a common mistake I see is people plug the -3 here and they plug it here, but they forget that there's an x over here on the other side too, and then they get all confused. So just remember, you have to substitute -3 in for all the x's. So you'll get -3 plus 17 on the left. This whole thing goes to 0. I'm going to write a 0 just to remind us what happened. This first term goes to 0. Then -3 here is going to give -6. Take away 1 is -7. So -7b. So what do we got? We got 14 equals -7b. So -2 is our value of b. And then we can do it again. This time we're going to let's do it in burnt sienna. Let x equal, the 0 here would be +1/2. So slightly annoyingly, this side is going to be kind of ugly. We can just call it 17.5 for now. And this is going to be ugly too. It's going to be, well, let's just call it 3.5a. And this part goes to 0. So to solve, you'll divide. If you divide, it'll come out cleanly. If we convert these to fractions, maybe it's easier to do the division, like if you don't have a calculator, and I don't have a calculator to give you either, then to figure this out, just make them fractions. 17.5 would be what? 35 divided by 2? And this is 7 divided by 2. So a pretty clean way to think about how to solve this is you just multiply by the reciprocal. 2/7, 2/7. And then you see the 2's cancel, 7's cancel, there's your A. These 2's cancel, and then 35 over 7 is 5. So we can see this actually does come out cleanly, even though it involved decimals. So we just get 5. And that means our final answer is going to be 5 over 2x minus 1. And with a negative b value, we'll just say subtraction instead of addition. We'll say 2 over x plus 3. Excuse me. Again, remember, what this whole thing means is that our original expression, this thing, is equivalent to this thing, right? I just don't want people losing sight of what the heck we're actually doing. The whole point of what we've been doing is we're supposed to be starting with this god-awful, ugly, rational expression, but then cleaning it up into a simpler, maybe 2, maybe 3, maybe 4, but it's just the sum or difference of a bunch of simple fractions rather than one big, ugly fraction. That's supposed to be the idea. But this is our answer. Bing. So now we get to the quadratic factors ones, which doesn't have to be harder, but maybe it is. Let's try it out. So right away, I see this is harder just because I have higher order polynomials that I have to factor. But this thing's cubic, and my coefficients are in a ratio of 1 to 1. It's literally 1 and 1. And these guys are in a ratio of 1 to 1. I guess I should say technically 1 to negative 1 and 1 to negative 1. But again, that points to this thing being factorable by grouping. So I've grouped the first two terms, grouped the last two terms. We can see we could factor x squared out of the first to be left with x minus 1. Over here I'm not factoring anything out, so technically it's like 1 times x minus 1. So then if you factor out the x minus 1's, you get x minus 1 and an x squared plus 1. Alright, so again, it seemed to be helpful to people to think about how, if this was x squared minus 1, right, then that's a difference of squares. You could factor further. You could have x minus 1 and then an x plus 1 and an x minus 1. But because this is plus, we just cannot factor any further. So for the first time, we see that we've got this denominator that has a linear factor, but it also has a quadratic factor that we just can't break down any further. And so that's fine. We just keep our numerator, factor our denominator as far as we can, and then we break this thing down. So again, this first linear factor will generate a fraction whose numerator should be a constant, so again just a. Then our quadratic factor will generate a second fraction whose numerator, remember we said it has to be 1 degree less. So don't get into the habit of just always going A, B, C, D, E. With a quadratic denominator, you need a numerator that's linear, which means you need a linear term like bx, and you also need a constant like c. So to model a linear expression in your numerator, you need a bx plus c. Okay, you need a coefficient on x and you need a constant. But that's it. That's the main difference. And now from here we would do everything the same. We're going to multiply through by this LCD. So we'll see it cancel out and we'll just get our numerator, the x squared plus 4x plus 1. We'll see the x minus 1 cancel, and so you'll get a times the x squared plus 1. Then the x squared plus 1's will cancel, and you'll get bx plus c, which really needs to be in parentheses, times x minus 1. Again, just to fill you in on how people screw up, people forget to put these parentheses. So then what do? they realized that let statements aren't going to work because there's literally no value of x that will make this equal 0. Psych. There are values that make this equal 0, but they're imaginary, so we can't use them, right? So we know that we would want to do this by system of equations probably, so they bring this down, they go x squared plus 4x plus 1, then they distribute this a, so they get a x squared plus a. Then, because they were sloppy, they look at this and they go, oh, bx, let me bring that down, bx. And then let me just distribute the c. And that, of course, is hugely wrong, because you're not multiplying the x minus 1 by just the c. You need parentheses around this. You should be multiplying x minus 1 by the entire bx plus c. And so now you're in a situation where you should be foiling. So shouldn't you be getting bx squared? And your outer would be negative bx. And your inner would be plus cx. And your last would be minus c. So we've screwed up pretty royally if we don't remember our parentheses. I just want to make that very clear. So be careful. So let me erase this garbage. Let me turn this back into navy blue. This shade of navy blue. These two blues are like identical practically. I'm going to have to work on my blues, guys. Alright, here we are. We said now, it's been a while since we did this method. It's been 31 minutes and 44 seconds since we did this method. This is now the method where we want to shuffle our like terms together. So we've got a quadratic term and a quadratic term. We want to combine them. We've got a linear term and a linear term, so we want to combine them. And we've got a constant and a constant, right? And by the time we're done doing that, we'll be able to pair our quadratic with the quadratic on the left. We'll be able to compare our linear with our linear on the left. We'll be able to compare our constant with our constant on the left. We're matching these things up. So where are we? We've got the x squared plus 4x plus 1. We can see that if I do ax squared plus bx squared, I'm going to have an x squared term whose coefficient is a plus b. When I get to the linear, I'm going to have an x term whose coefficient is negative b plus c. And then the constants are literally just going to be an a plus a negative c, so minus c. And again, throw parentheses around that. So like I said now, from here we want to generate a system of equations. I shouldn't use black. I like to use black for this. We'll use red. Our system, there's going to be 3 equations, and those 3 equations come from your 3 coefficients, right? So what I mean is our quadratic coefficient here, there's nothing there, so it's a 1. So you pair that up with your quadratic coefficient, and you now have an equation where a plus b must equal 1. Okay, again, why am I leaving all this space? Well, because there's a c variable too. So I want like a first column that's all a's, a middle column that's all b's, and then a third column that's all c's. So when there is no c, I leave space. Anyway, we do it again. Red, orange, yellow, green, blue. We can do blue. I've got a linear coefficient now. That's going to generate my second equation. I've got a linear coefficient over here. So my equation's going to be, let's actually write it in blue. It'll be a negative b, put that in the b column, plus c, start our new c column, and then set it equal to that coefficient, which is 4. Then finally, purple. We haven't used purple yet. We've got our constant, which is a plus 1. We've got our constant, which is an a minus c. So that means we can now fill in a third equation into our system where we have an a minus c. So a is first, minus c goes third, and that equals 1. So you've got this big system now, and I know for some of you guys solving systems is not your forte, so we'll go over this and hopefully it'll be okay. But we would want to solve this the same way we solved the other system from before, I basically am looking to try to add equations together to get variables to cancel out. And you know, there's a b and a negative b right here that look pretty ripe for the pickings. If I added equation 1 to equation 2, those b's would go away, and I'd have an equation involving only a and c. Now these c's are ripe for the pickings too. I could add them together and cancel the c's. It doesn't matter which one you do. You just have to make a choice and do it. I'm gonna cancel the c's, I think. Just visually it makes more sense. I'm gonna put my plus sign. If this is equation 1 and 2 and 3, I'm adding only equation 2 and 3. Not equation 1 is just there. I'm adding 2 and 3, and I'm going to get an a minus a b. The c's are going to cancel, and so a minus b is going to equal 5. Now conveniently, look at equation 1. It only involves a and b. So what I can do basically is I can take my 3 variable system, and I can borrow this 2 variable equation, the a plus b equals 1, and I just generated this new equation that's only a and b, so a minus b, that thing equals 5. And so by adding these equations and canceling c, I've made myself a new 2 variable equation. I already had a 2 variable equation, so I've essentially reduced my 3 by 3 system into a 2 by 2 system. And then I continue working on that now. And I'm hoping it sticks out like a sore thumb that if I just add these as is without doing anything else, the b's will cancel. And I'll get myself a 2a that equals 6, which means that a is 3. And then the rest from here should be cake, because once I have a, I can just plug that in pretty much anywhere. I'm going to use this equation. Plugging in a means I now have 3 plus b equals 1. So subtracting 3 tells me that b is negative 2. And now, if you want to find c, then go back to your original system that had some c's in it and pick either the second equation or the third. It doesn't matter. I know that a is 3, so plugging 3 into this equation would allow me to solve for c. But I also know that b is negative 2, so plugging in negative 2 into this blue equation would give me a way to solve for c also. So the ball's in your court. Again, just make a choice and do it. It doesn't matter which way you go. So with that said, I'm going to do, I don't know, the purple one. So yoink, yoink, yoink. In the purple equation, I can go 3 minus c equals 1. So I guess I would add c. I'd get 3 equals 1 plus c. Then I subtract the 1, and 2 equals c. So we did it. We've got all of our values now. So just to clean this up a smidge. That means we can write our final answer now. Remember, our final answer is going to come from this expression that we worked so hard on. So here's our partial fractions. So that's going to be our answer. And we just want to make sure we plug in our values. So if a is 3, then we're going to have 3 over x minus 1. And then for our linear, we're going to have negative 2 plus 2. So we can do that. Kill that, kill this. So we're going to get 3 plus, we said, negative 2 plus negative 2x plus 2. Alright, again, you know, I don't want to be too annoying. So if you left your answer like this, that would be fine, and I wouldn't mark you down. Although, sure would be nice if you guys could just go with me on my hatred of leading negatives. So factor out a negative, you'd now have 2x minus 2, and then you can let that leading negative just turn the plus into a minus. So really the best answer is 3 over x minus 1 minus 2x minus 2 all over x squared plus 1. and then box that up. That's the best possible answer. Okay, I hope you get it. Moving on. Let's do 5. All right. Yeah, okay. So this thing says part 2 quadratic factors. Then we go here. And what it doesn't say is this should be called part 3. I wonder if your homework says that and I just failed to. Maybe I just failed to bring that with me. But it really should say part 3 repeated quad factors. Because we know that we deal with repeated factors differently. So let's make sure we do this right. Let's make sure we remember that this is a repeated quadratic factor. No big deal. Maybe it is. Some people definitely expressed a lot of confusion about this, but basically you want to view this as 2 factors. It's the same factor, but it's squared, which means we've got essentially this factor times itself. We said the way that you handle these repeated factors is you'll go x squared plus 1. Then you'll need x squared plus 1 again. And what you need is you need every single power that goes from the given power all the way down to 1. So with 2 you just need 1 and 2. But if this thing was like to the power of 8, then you would need you'd need this thing to the 1, and then this thing to the 2, and then to the 3, to the 4, to the 5, to the 6, to the 7, to the 8. You would need literally 8 fractions where each denominator has this base to every single possible power from 8 all the way down to 1. Okay? So, when you think of it like that, we're getting off the hook pretty easily. We're going to need an x squared plus 1 to the 1, and we're going to need an x squared plus 1 squared. But that'll be it. That'll be our decomposition. And since this is quadratic, we need a numerator that is linear. So we know we'll fill this in with an ax plus b. Now the tricky part again is over here. Technically my denominator is still quadratic. It's just a repeated quadratic. So the fact that if you FOIL this thing out, you'd have an x to the 4th plus la 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 la, it doesn't mean you put a cubic up here. You don't. You're going to still just think of this thing as a quadratic, which means my numerator should just be another linear of the form ax plus b. But we need new variables, so it'll be cx plus d. But this is the correct setup. And then from here you do what we always do. So what we always do is we multiply through by the LCD. The LCD being the x squared plus 1 squared. So when that thing distributes through, it's going to multiply all the way over to here and just cancel the denominator, giving me the 2x cubed minus x squared plus 5x. Then you get the ax plus b. And one of the x squareds plus 1s cancels, but you still have another x squared plus 1. That's going to multiply the ax plus b, so you'll have to FOIL that out. Then here, this whole thing cancels, so you get the cx plus d. Okay. Alright. So again, we can't really solve this thing by the method of writing let statements because we're in another position where this irreducible quadratic has only imaginary zeros, so there's just literally no way to make this thing equal 0. And even if we did, even if this became 0, it would only kill the a and the b. You'd still have c and d left over, and you wouldn't be able to solve the equation because you'd still have one variable too many. So, literally that method will not work. So you have to use our method of writing a system, which means, bring this down. And you expand this, so we're foiling. So take the ax and distribute it in, you'll get an ax cubed. Distribute the a, you get plus ax. Now that the a has been distributed onto both terms, you distribute the b, you get bx squared. And distribute the b, you get plus b. Now the good news is over here, since everything canceled, you just have cx plus d. We don't have to do anything with that at all. So everything's now fully expanded. Now we, this is where we would start grouping our like terms. But, well, no buts. Let's just do it. No buts. Let's go purple. We've got a 2x cubed minus x squared plus 5x. You cats are not likely to bring highlighters, so I'll stop using a highlighter for a second. But, you know, single well, I don't know, maybe 3 underlines since my exponent is 3. But that's the only cubic. So you just bring it down, ax cubed. Then you look for your quadratics, do a double underline. And that's the only quadratic, so you just bring it down. Then you look for your linears, do a single, single. So there they are, I see them. It's going to be an x with a coefficient of a plus c. And then for the constants, maybe just don't do anything. The ones that aren't underlined are the constants, so plus bd, b plus d. There. So the great news is, just like the one we did in class, there's only this one cubic term, so we now know instantly that a just straight up equals 2. There's no math to do. We can just see that a must be 2. By the same token, since there's only one quadratic term, we can see that b just has to be negative 1. Then we've got our linear. Okay, fine. A plus c is 5. Yes, yeah, sure. A plus c might be 5, but we already know that a is 2. So 2 plus 3 makes 5. So we now know that c is 3, right? We solved that. And then the one thing that might screw somebody up if they're not paying attention is we've got this constant, but there's no constant. There's nothing to pair that up with. But that's fine. Please tell me you guys know that if there's no constant, it just means that the constant is 0. So b plus d must be 0. So we could still write a system. It seems like kind of a moot point. But our first equation would literally be a equals 2. It would just be the answer. And the next equation would be b equals negative 1. The next equation would be a plus c equals 5. And the last equation would be b plus d equals 0. So, okay. We got freebie right here. We got another freebie right here. Then using a, we can find c. You just go 2 plus c equals 5. So c must equal 3. Is this like lime? You guys can see this lime green color, I hope. If you can't, tell me tomorrow in class. Not tomorrow, because nobody's going to watch this tonight. But now you got the b plus d, so use the b value. That means negative 1 plus d equals 0. So adding 1 tells you that d equals 1. And so now, lo and behold, we've got all 4 of our values, and we're basically done. We can just write our partial fractions now. So we wanted a plus b. That'll be 2x minus 1. So 2x minus 1 will be the numerator of the x squared plus 1 fraction. And then 3x plus 1 will be the numerator of the x squared plus 1 squared term. But there's your partial fraction decomp. That's the best we can do. You can't break that down any further, so there's your answer. Okay. This video is coming up on 50 minutes. Where do I break? I think I break here. Oh. Part 3 is repeated linear factors. So actually, number 5 belongs with part 4 with repeated quadratic factors. 5 should be a part 4 question. Not that that matters. Like, who cares? Obviously, when you guys get your quiz, everything will be shuffled together. You know, the hardest question might be first, right? So you better just be able to recognize what you need to recognize without friggin' headings, right? It's not going to be a heading telling you what each question is. But yeah, I'm going to break here. I'll get this video posted so you guys at least have this to go on, and then we'll make a second video that's all the rest. Yeah, that's what I'm doing. Okay, bye.